Good morning, everybody. My name is Ryan Laren. I'm working under Dr. Wayne Strasser at Liberty University using computational fluid dynamics to develop a punctuated equilibrium model for polymerization reactions with complex chemistry and a rigorous CFD model in order to optimize a $45 billion chemical industry that my colleague here mentioned. We're going to talk about the current state a little bit first. You will notice a significant amount of overlap with Elijah's presentation, so I won't bore you with all of that, as you've already seen, but any details that he didn't touch on that are important to this, I will. So, of course, low-density polyethylene is a super important common type of plastic backing a $45 billion industry, using things such as the ones listed here, plastic bags, toys, liners for milk cartons, you name it. In addition to autoclave reactors, it can also be developed in tubular reactors. The main differences being throughput and variability of the polymers at the end of the reaction. So autoclaves are more customizable with a lower throughput, while tubular reactors have higher throughput, lower customizability. Tubular reactors are actually cooled with a jacket, unlike the autoclave reactors, but they both operate at high pressures and temperatures. You see images of both of those right there. And so, as Elijah mentioned, these are typically, you can run experiments, but that is costly, risky, it takes a lot of time. So lots of people turn to softwares. The standard in the industry is just a chemical software such as Aspen, which we validate some of our numerics against. They use the continuous stirred tank reactors, which assume perfect mixing. They're cheap, but they provide those approximated results, which is all well and good. But if you want to look at any sort of spatiotemporal gradients within the flow, that is where CFD is needed. So these CSCRs are not inherently useless because they can be used as sort of a proof of concept in CFD as you're developing kinetics and developing a project before moving into a larger reaction. So as I mentioned, CFD can be used to capture the spatial gradients of things like species concentration, temperature, viscosity, and more. You can see a contour of the temperature in a vertical slice of one of our reactors and one of our zones of an autoclave reactor. And if you're using a CFD CSCR or a normal CSCR, you're not getting all this refinement and you're losing insight into localized phenomena, potential reactor suboptimal performance, because all these gradients can affect the reactor efficiencies or rates. So CFD is needed if you want to look into the mixing or any of these gradients. Like Elijah mentioned, if you want to simulate a full reactor in CFD perfectly for polymerization, you would need a mesh on the length scale of the molecules themselves, which is completely ridiculous. And again, you need a PDE for each polymer chain length, which can be theoretically infinite. So that's not going to happen. Even limiting it to a couple thousand, which is unrealistic, is still going to give you an extremely slow simulation. So the method of moments coming in, as again Elijah mentioned, we all know this now. We're pros on it due to Elijah's amazing presentation. But essentially, simplifying this infinite set of equations down to a finite set of moment equations. But each of these moment equations deal with live and dead moments. Each of these, as he mentioned, has zeroth, first, and second moments. The zeroth moments of the polymer give information about how many entities are present total. The first moment gives information about the cumulative size of the mixture. So for polymers, that would be like the molecular weight distribution. And the second moment gives information about the breadth or variability of that distribution. So combining all those, you can statistically reconstruct the molecular weight distribution. And with some extra effort, which is outside the scope of this project, you can reconstruct the distribution of a polymer specifically, which has a little bit of a shoulder rather than just a straight bell curve distribution. So where we're left off in the current state, through the efforts of Yoder and Strasser and Terman and Strasser, we now have a system with computational fluid dynamics, with an industrial plant scale model, with complex chemistry, with a method of moments, and we have a simulation that is almost capable of reconstructing a molecular weight distribution. That's the end goal. With that final piece, we would have a simulation that's one of its kind, the only one of its kind, rather, um, with all those components. And that brings us to a punctuated equilibrium model, or a PEM. Because while that simulation sounds amazing, that's the final piece of the puzzle, it is prohibitively time consuming at the moment. Even if a reactor's flow field reaches quasi-steady state, the kinetics may be extremely far from convergence. If we assume we get around 2.7 seconds of flow time simulated each real Earth day, and if we look at this plot here, we simulated about 150 days up into this red vertical dashed line and used a fit to extrapolate some extra data. And we're learning that we need around 2 years of simulation time on an HPC cluster to reach a final solution. And that's, we wouldn't want that. So with a punctuated equilibrium model, we can temporarily freeze or fix equations not used during kinetic development if they have reached quasi-steady state. You will have unaffected accuracy. So let's say our flow field is completely converged. We can freeze the equation solving continuity and momentum. That won't affect our kinetic convergence, but it'll speed up our solver. And so it won't affect the number of time steps to reach convergence, but it'll get to that number of time steps more quickly if instead of solving 5 time steps for every Earth second, you're solving 10, for example. So here are our governing equations for incompressible flow in vector notation. All familiar with this, so I won't spend much time here. Continuity, momentum, and energy. And this is an example of what a PEM simulation could look like. This is completely arbitrary data, but just sort of to visualize what's going on here. So let's say we pause flow, turbulence, and the metrics used to calculate polydispersity index. As you recall, that was the one that was taking forever. So that's sort of our main metric here. If we pause all of those at this peak, it's going to be unchanging for a little while, and the solver is going to be moving significantly faster without having to solve those equations. And theoretically, you could leave this paused all the way up until you finally want to get an answer. But in a simulation taking so long, maybe you want to check on it every now and then. So you'll intermittently toggle whether they're on or off. So off, they'll quickly adapt, see where you're at, turn them off, and this whole time, your simulation is running faster without affecting the accuracy. But again, it's not going to take maybe fewer time steps to reach that answer, but it's going to take significantly less Earth time. So as I mentioned, in project development, we're going to want to use a CSTR instead of just plugging this into a full reactor. This actually grew into a completely different study that is in a paper in preparation. We started with a CSTR with 65,000 coarse tetrahedral elements. We wanted it to be as diffusive as possible to get as near to perfect mixing as possible, but even the CSTR would take around 2 weeks to reach convergence. And when we are running dozens of tests, that's not optimal. So we reduced it down to around 4,100 hexahedral elements, since they're just more efficient with space. And that provided good results, had little effect on accuracy, but sped us up a lot. So we wanted to see how far we can push it. We eventually went down to 1,300 elements, then down to 29, then down to 3. And it should be noted that each of these mixing zones has the same volume, so we're not changing any of the simulation parameters. But and recently, before this conference, we actually got a singular cell CSTR working that we're currently testing right now. But this resulted in a drop from 2 weeks of simulation time down to about 18 seconds. So we're very happy with that. And again, that paper is in preparation. In order to judge quasi-steady state, QSS, we define a window of some amount of time steps, look at the range of PDI within that window, and if that range is under a specified threshold and doesn't leave that threshold to the end of the data, then we're at QSS. If it's not, if those requirements aren't met, that window simply moves forward in time, and we run those calculations again. Here, we can see the PEM design of experiments, featuring all of the equations to be disabled or kept enabled, flow and turbulence, energy, all of our species transport, and then user-defined scalars, which is how we implemented those live and dead moments, which is how we calculate our polydispersity index, weight average molecular weight, and so on. So disabling this bottom row is what gets us those flat areas in PDI. And when I say flow, I'm referring to pressure velocity coupling, aka not solving for continuity or momentum. But since the flow field's at quasi-steady state, if we're just freezing an already converged solution, that shouldn't affect the kinetics. And you'll notice that some of these have the same combinations of things disabled versus enabled. If that were the case, maybe another test was gone, varying time step or mass diffusivity within the simulation. But um, we'll see that that's not as important as you might think. So just some results. This is for a 1500 time step benchmark. So we only care about solver rate right here. We're not really looking at time to reach a kinetic converged solution. So you'll see some of these are highlighted, which I'll get into in a second. But this bottom row with normalized data is what we want to really look at. So obviously, with a base case in our 3-cell CSTR, we have a normalized time of 1, of course. So it's all normalized by the base case. Now, case 2, with only flow disabled, rather, is about 2.5% faster. C6 is about 5%, and C9 is about 8%. That doesn't sound very impressive, and it's not, but bear with me, I promise it does get a lot cooler. If we look at a time to reach kinetic convergence, this isn't the cool part yet, these are still small numbers, bear with me. C2, C6, C9 again, you'll notice these are the exact same numbers as above, which is good. That's proving that pausing these equations doesn't affect the amount of time steps to kinetic convergence. So when we're normalizing by the same scale, we are keeping that consistent. So you also notice that some of these are X'd out. That is because these PEM cases diverged, and the commonality between all of them is that they had either the species transport or the energy equation disabled, indicating that both of those are necessary for the kinetics to progress without blowing up. And you'll notice for C9, that number does not match. That's because while in C9 we can keep a flat PDI curve, we're eventually going to need to re-enable those UDS equations. And so for about 50% of the simulation, we'll drop back to C6's solver rate, which is why these don't match. Here, the UDSs were disabled the entire time. Here, we had to re-enable them for some amount of time. So lots of data here, but the main takeaway is that freezing does not affect kinetic time steps to convergence, nor does it affect the accuracy, and we need the energy equation and species transport. Here's an example of a base case. So with no PEM, between this and the next slide, we're just going to look at how effective the PEM is. So base case reaches QSS at around 80 seconds, and with C9, you'll see the flat area, the re-enablement, and then down to QSS, saving about 5 to 6 seconds. So you just look back and forth, and it moves around a little bit. So again, still not impressive, but here's sort of the money plot. So we tested all of that on all the previously mentioned CSTRs, plus a couple more. The 65,000 CSTR was adapted to around 200,000 cells, and the 4100 cell was adapted to around 20,000, just to get some more data in here. And on the y-axis here, you can see the percent speed increase from the base. So if case C2 is 10% faster than the base, you'll see it at 10 on this plot versus cell count. So as you can see here in our 3-cell CSTR with all the puny improvements, as you increase cell count, you are increasing the amount improved up to around 50% for C9 with the 200,000 cell mesh. And we put fit curves on these up to 5.7 million cells because that is our full reactor cell count. And that predicts speed increases of about 100, 101, 105%. So that is much better, and we'd be taking off a potential year from our simulation if this is scalable. And so you'll notice here that the cases themselves kind of start to separate and then conglomerate back together. That was weird. We wanted to make sure it wasn't just a byproduct of the fit curve. So we shows it here. Both y-axes are just ratios of C6 to C2 or C9 to C6, just showing that as cell count increases, the difference in their improvement also declines. And that happens before even the fit curve. So that is not just numerical error of the fit curve. So in conclusion, pausing the calculations that have reached QSS, like flow, like turbulence, do not affect the kinetics themselves. Calculations of polymer scalars, or those live and dead moments, can be paused and re-enabled. since their values do not contribute to the reaction. And as they're re-enabled, they readapt to this new species concentration and temperature field, converging much more quickly. And using the PEM we have now, we are projected to take around a year off of our full reactor simulation to QSS. And we are also exploring other methods to speed this up, because even a year is still a long time to simulate for one result. So in the future, we are currently running our PEM in larger meshes to ensure scalability, but we need to test and more models with varying cell counts, because we just want to make those stronger fit curves, be more confident in our money plot. And we want to, of course, implement into the full-scale reactor model at the end of all this. Thank you for your time. Are there any questions? There it goes.
So you mentioned that you are freezing the flow field. So that's like kind of a big part of what you're doing here. So if you're freezing the flow field, what is, I guess, like the main benefit here as opposed to something like a CSCR? It's just that you have, non-uniform flow properties that are just frozen as opposed to being like perfectly mixed, or
Yeah, so in a CSDR, there really is no benefit of a PEM. Because you're perfectly mixed, you don't care about all the gradients. But this study is mainly just the proof of concept to be put here, because in here, you do care about the gradients, so you can't just increase turbulence like crazy to make it perfectly mixed. So you care about the gradients here, but this simulation is insanely slow, and the PEM is there to increase that solver rate.
How, you've been like reducing it a lot of the time. At what point would you like to say you keep reducing it? When would it be like, okay, like keep reducing it?
Whenever we run out of ideas to reduce it further.
One more quick one. If you're freezing the flow field, and we were talking about hot spots in the talk before, and that those are kind of regions that are not, they're not mixing well, and then you have this exothermic reaction. If you're freezing the flow field, how are you avoiding like hot spot development?
That's a really good question. When we implement this into a full reactor, there are multiple reactors we're working with. Another study that we currently have going on, obviously, from Elijah's work, there's kind of a whole branch of polymerization. Another branch of that is simulating decomposition, hotspots, thermal runaway more accurately, instead of just, right now we're assuming anything above 300 is kind of leading to runaway. But we're going to incorporate those decomposition kinetics in there to, as someone asked a question about it, I forget who, see how these hotspots develop, or if they're just solid spheres moving around. Those kinetics will then be able to tell if they lengthen out, stretch, or become more diffusive. But I suppose in a simulation with the frozen flow field and a converged flow field that isn't really changing anymore, QSS, I suppose we're kind of assuming that hotspots wouldn't form in that flow field already.
Really, what we're doing, as far as I understand, what we're doing, maybe I don't know, but you're still allowing convective cooling by freezing the flow field. You're not turning off transport phenomena. You're just saying, for the next few time steps, I'm going to not care what's changing in the flow while I look at smaller timescale structures that's happening in the chemistry. Okay. While that stuff's really not going to take up a long time step. So we're still allowing the convective cooling where heat to transpire. I think we might have to hold that